What is the difference between weight and mass? And how come on the moon you weigh at least 10 times lesser than you weigh on Earth, but you have around the same mass? And what exactly are free body diagrams? And how can you use them to solve nearly any physics problem regarding force? That's what we'll be going over in today's video regarding free body diagrams and the topic of weight versus mass. So let's get started. First, let's establish the distinction between weight and mass. Okay? Mass is the amount of matter in an object in kilograms, constant everywhere in the universe. So think about mass as how much stuff you have. If you eat more or you grow, you're going to have more stuff. Okay? But that's just how much content you have, how much body, what are you made of? How much do you have in you? Which is measured in kilograms. But weight is actually the force of gravity, which, if you remember, was mg. So your weight is actually your mass times the gravity, which is, acceleration due to gravity, which is 9.81 meter per second squared. So whenever you say I weigh, you should actually be saying I mass, although that's not what we say, right? And your weight is actually your mass. The force of gravity is your weight. So mg is your weight. And weight is measured in newtons, right? Because it's a force of gravity, it's not kilograms. It's not how much stuff you have. It's your force of gravity. Changes with local gravity. Local gravity means, for example, Earth's acceleration due to gravity is 9.81, right? Meter per second squared. But on the moon, the same thing would be g is equal to 1.6. So Fg is equal to mg would be different, right? Because you'd have to multiply by a different. So if you had m is equal to 10 kgs here, Fg is equal to 10 kgs times g, right? And g could be 9.81, which would give you a larger value, or it could be 1.6, which gives you a smaller value. So you see how weight is different. It's just how much force the gravity has on you, which depends on the acceleration due to gravity on that particular planet, right? Like on the moon, the acceleration due to gravity is lower. That's why your weight would be lower. But your mass is going to stay the same. It's just how much stuff you have. Your weight is the force of gravity acting on you. So now let's move on to free body diagrams. Let's go over how to draw a free body diagram, okay? Free body diagrams can only be drawn for one object, okay? You can draw multiple, but each one has to be for one particular object. You have to represent it as a single dot or box. So the dot over here is the origin point. That's the object itself, okay? Draw every force acting on the bots, right? On the bots, not outside forces that are not acting on the bots, as a labeled arrow from the center. So forces are arrows here, okay? And you label them appropriately. Like over here, this could be normal. This could be mg, or force of gravity. This could be force applied. This could be force, friction, kinetic, right? You label them so you know what forces they are talking about, what you're talking about, what are the constituents of the net force acting on this object. And then you choose the axes aligned with the motion. So this is a bit more complicated, and you'll get it more when I go over ramps. But for example, if you're over here, then you could consider this the leftward direction and this the rightward direction, right? And tilt your regular axes all the way like this. But don't worry about that too much for right now, okay? We'll go over that later. If it's troubling you, then keep in mind that we'll go over it later. Don't concern yourself over it. And never draw a force twice, and never omit a force present, unless we say it's negligible, right? Like if you say air resistance is negligible, don't draw that. But if the force is present, you need to draw it. And if it's considerable, you need to draw it. So also, never draw a force twice, right? Why would you draw a force twice? Doesn't really make sense. And one common error that you need to concern yourself with regarding free body diagrams is that drawing a force the object exerts on something else instead of a force acting on the object. So if the force, or if, for example, we had a system between Earth and a block on Earth, then we wouldn't say Earth is pulling Earth, the block is pulling Earth up, right? We would only say Earth is pulling the block down. We wouldn't, so not the force the object exerts, right? So not like electromagnetic, or that's all charges and stuff. It's just the force acting on the object itself. So let's draw a free body diagram for a hanging block. Okay? Imagine a block hanging like this. And what's the free body diagram going to look like for this? Well, we know mg is going to pull it down. So I'm going to draw a dot here. This is my object. Okay? I'll denote mg in red. Force of gravity is equal to mg. Okay? So that's the mass of the object times gravity. And that's going to be pulling it directly down. And then my other force is going to be, do I have a normal force here? No. But what's keeping me up here? A string, right? And remember what force is associated with strings? Tension. This tension is tightening the string, so it keeps the block still on the string. It keeps it still in the swing, right? It is not falling down. If it had to fall down, mg would have to be greater than tension. So if it's staying there, that means mg is equal to tension, right? It's not accelerating at all. It's staying there. Newton's second law. So that's why motionless, which is net force is equal to 0, and T minus mg is equal to 0. Because if you consider this the positive direction, and this the negative direction, then T is in the positive direction, right? Minus mg, which is in the negative direction, and that has to be equal to 0. Because if it equals something else, the block would be accelerating. Because net force is equal to 0, net force is equal to ma. Because m is constant, if net force is something else, that means a has to be playing a role, right? If it's not something other than 0. So that means you have to have an acceleration, which we don't have here. So T is equal to 5 times 9.8. So because the block is 5 kgs, times 9.81 meter per second squared, or 49 newtons. As always, we'll go over more advanced variations of tension problems later on, because there's way more ways this could get pretty complicated and tricky. We'll look at that, okay? So don't let that scare you. Alright, so let's practice drawing some free body diagrams. Draw and label the free body diagram for a book pushed at constant velocity across a rough table by a horizontal hand force. So I want you to try these out first, right? That you always need to take a pause and try these equations out yourself. Try these questions out yourself, because you're only going to learn that way. So try it out first. Alright, I'm assuming you gave it a try. So let me try the table in black actually, or green is fine. Right, so we have a table here. We have a book here. Red book here. Okay, red book. And it's being pushed at a constant velocity across a rough table by a horizontal hand force. If it's a constant velocity, remember what that means, right? that means net force is equal to 0 because it's not accelerating. And if it's a constant velocity, that means acceleration is equal to 0. Run over to Newton's second law. So my free body diagram, this dot would be the book. So I'm pushing it across the rough table. So my force applied would be in this direction. Or it could be the other way, just some direction, right? I'm pushing it across that way. And then my force due to friction would be acting this way. And it'd be kinetic friction, right? Because it's in the direction opposing motion. Since this is the motion, this is the direction opposing motion. And then we know mg is acting on it, force of gravity mg. And what force is keeping it upwards? Normal, right? And if F kinetic, and F applied balance out, then net force is 0 and it's just moving at a constant velocity, not accelerating. So that's pretty neat, right? And rough table here, that's rough, it just means that the table has a lot of friction. That's why force friction kinetic is matching force applied here. Okay? Free body diagram for a thrown ball. Draw and label the free body diagram for a ball in midair after being thrown straight up, ignoring air resistance. Okay, so the guy throws the ball straight up. Okay, it's in midair after being thrown straight up and ignoring air resistance. The only force acting on this is mg, right? Because we're ignoring air resistance. If it's in the middle of air, what are the only forces acting on it? Only mg, so that's why the ball is in free fall. This is also a good example of why objects that are even moving upwards can also be in free fall. Not just objects moving downwards, right? Because you might think, okay, if I throw an object and it's moving downward, the only force acting on it is gravity, so it must be in free fall. I mean, I'm not saying there's anything wrong with that. But also, if an object is moving upward, it can still be in free fall. Okay? How's that possible? So your hand gives a velocity, right? Second you touch it, it has a force applied, and your hand gives a velocity. So the velocity is nibbled at by the gravity. But when it's still moving upward in the air, what force is pulling it down? What force is changing its arc and decelerating it? So it's moving, it moves up like this, and then it's going to go downward, right? What force is doing that? Only gravity. Even though it has a positive velocity, it has a downward acceleration, which is reducing its positive velocity and making it a negative velocity. Okay? So it goes like that. So still going to be only mg, or force of gravity. That's a good example for why objects even with upward movement can still have free fall. Okay? It's not just objects with downward movement. Whoops, went too far there. Alright, so let's try drawing the mass and weight on another planet. A 2 kg object weighs 19.6 newtons on Earth. Find its mass and weight on a planet with g is equal to 24.5 meter per second squared. Okay, so first we know force gravity is equal to mg. Okay, this is weight. So 2 kg object weighs 19.6 newtons on Earth. That means 19.6 newtons, which is force of gravity, or weight, this is weight, right? Weight is force of gravity, is equal to 2 kgs, which is the mass, times 9.81 meter per second squared, right? Find its mass and weight on a planet with g is equal to 24.5 meter per second squared. Mass is always going to stay the same, so it's still going to be 2 kgs on planet X, let's just say. And weight, though, that's going to change. That's W is equal to mg, right? Or force gravity is equal to mg. So that's going to change to, which is going to become 2 kgs times 24.5 meter per second squared, which is the acceleration. And if I pull out my calculator to do this, right, this is going to give me, and this is very strong attractive force, right, because gravity for Earth is only 9.81, so this is going to be 49 newtons. And that just means that this planet pulls you down way harder. Okay, that's why you feel like you're heavier, because you can't jump as high. You don't feel as light. So mass is always constant, but how heavy you feel, how much like flexibility you have, depends on the planet and how much force is pulling you down, or letting you stay up. So that's why you feel really light on the moon, right? Because there's a lesser acceleration due to gravity. That's why you can move higher and you won't be pulled in with the same force, because force of gravity is lesser as lesser acceleration due to gravity. Right. And next time we'll be going over inclined planes and how to solve free body diagrams, as well as force problems and Newton's second law problems involving these ramps and inclined planes. So make sure to look out for those. Thank you for listening, and make sure to give me a like and subscribe if you believe I helped you, and keep in watch for my future content.